Objective 2. Use the multiplication rule for independent events. Suppose that you flip a fair coin twice. What is the probability that you obtain a head on both flips? That is, a head on the first flip and a head on the second flip. Now, if H represents the outcome of heads and T represents the outcome of tails, then we would have the following sample space of this experiment. We'd have HH, HT, TH, and TT. Now, there is one outcome with both heads. And so we can see here that there is that one outcome. Okay. Now, because each outcome is equally likely, we would have the following. The probability of heads on flip 1 and the heads on flip 2 is the number of outcomes that has heads on flip 1 and heads on flip 2, which is one of them. And then we're dividing it by the total number of the sample space, which is 4. Now, we may have intuitively figured this out by recognizing that the probability of a head is equal to 1 out of 2 for each flip. So it seems reasonable that we can say the following. Looking at the same probability, okay, we can say that, okay, well, what is the probability of heads on the first flip? Well, that's 1 out of 2. Okay, and then what is the probability of heads on flip 2? Well, that's 1 out of 2. So we're going to multiply them together. Well, what's 1/2 times 1/2? Well, that gives us 1/4. Now, because both approaches result in the same answer, we can conjecture that the probability of E and F is equal to the probability of event E times the probability of event F, which is true here. So now we're introducing the multiplication rule for independent events. Okay, so if event E and event F are independent events, then the probability of event E and F is equal to the probability of event E times the probability of event F. Okay, so let's take a look at an example. Computing probabilities of independent events. Okay, now in the game of roulette, the wheel has slots numbered 0, 0, 0, and 1 through 36. Now, a metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 17 2 times in a row? Now, let's take a look at the approach. Now, the sample space of the experiment has 38 outcomes because we have 36 plus the 0 and the 0, 0. So that means we have 38 outcomes. Now, because the outcomes are equally likely, we use the classical method of computing probabilities. In addition, we use the multiplication rule for the independent events. Now, the events 17 on spin 1 and 17 on spin 2 are independent because the ball does not remember it landed on 17 on the first spin. So, this cannot affect the probability of landing on 17 on the second spin. Now recall that there are 38 possible outcomes. Remember, there's 36 plus that one and that one, which is 38. So the probability of landing on 17 is going to be 1 out of the 38. Because the events 17 on spin 1 and 17 on spin 2 are independent, we would say the following. The probability of 17 on spin 1 and 17 on spin 2 is the probability of 17 on spin 1 times the probability of 17 on spin 2, because again, they're both independent. So we have 1 in our numerator, and 1 over 38 times 1 over 38 is equal to 1 over 1,444, which is approximately 0.0006925. Now, if we round this to the 10,000th place, so we're going to convert that 6 to a 7, so we're going to round this result to 0.00007, which is read 7/10,000ths. So how do we write that as a fraction? Well, remember that if we want to convert this to a fraction, we know that that 7 is going to be located in the 10,000th place. So therefore, we would expect the ball to land on 17 twice in a row about 7 times in 10,000 trials. Now, we could also extend the multiplication rule to 3 or more independent events. That means that we can have event 1, event 2, event 3, all the way to event subscript n are independent events. Then we would say the probability of event 1 and event 2 all the way to event e subscript n is taking each probability and multiplying them together. So the probability of event 1 times the probability of event 2 all the way to probability of event n, or the nth event. Now, let's take a look at this example here. It says that the life expectancy, so the probability that a randomly selected 24-year-old male will survive the year, is given. And it's given by the probability that randomly selected is 0.9986, according to the National Vital Statistics Report, Volume 56, Number 9. Now, the first part of the question says, what is the probability that 3 randomly selected 24-year-old males will survive? Now, it is safe to assume that the outcomes of the probability experiment are independent because the males were randomly selected. So that randomly tells us it's independent. Therefore, there is no reason to believe that the survival of one male will affect the survival of the other males. So we're going to use the multiplication rule for the n independent events. So the probability that all 3 males survive is taking the probability that the first survives and the second survives and the third survives, which means we're going to take the probability the first survives times the probability that the second survives times the probability that the third survives. So what we're taking here is we're taking the probability that we have given in the problem here, okay, which is 0.9986. So we're going to multiply all 3 of them together to give us that result that we get, which is 0.9958. Now, if we round this to 3 decimal places, we would get the following. We get 0.996. Again, converting this to a fraction is 996 over, since the 6 is in the thousands place. So we would say that if we randomly selected 3 24-year-old males 1,000 different times, we would expect that all 3 to survive 1 year in 996 of the samples. Okay, let's take a look at the second question, part B. It says, what is the probability that 20 randomly selected 24-year-old males will survive the year? Now we're selecting 20. So we're looking at 20, okay, that are going to survive, randomly selected, that will survive the year. Again, using the same number from the previous step. Now, it is safe to assume that the outcomes of the probability experiment are independent because the males, again, were randomly selected. Therefore, there is no reason to believe that the survival of one male is going to affect the survival of the others. So in this case, we're going to use the multiplication rule for the n independent events. So we're looking for the probability that all 20 survive. Now remember, the probability that the first survives all the way to the probability that the 20th survives. So we're going to take the probability of the first survives times the probability that the second survives times so on to the 20th, the probability that the 20th survives. So what we're doing here is we're taking that value, 0.9986, multiplying it by 0.9986 all the way 20 times. So that means we're multiplying this 20 times. So what we're doing here, we're going to shorten our mathematics and say that we're going to take this number that's the probability of 0.9986 and we're going to raise it to the power of 20 because technically that's what we did in the previous step. We're taking each value and multiplying it 20 times. So when we do that, we get approximately 0.9724. So there is the probability. So again, if we round this to 3 decimal places, we have 0.972, which is the same as 972 divided by 1,000. So then we would answer the following question. We would say, if we randomly selected 20 24-year-old males 1,000 different times, we would expect all 20 to survive 1 year in 972 of the samples. Okay, next example. Suppose that events E and F are independent. The probability of event E is given by the number 0.7. And the probability of event F is given by 0.6. What is the probability of event E and F? So we're looking for the probability of event E and F. Now, what we're going to do is we're going to use the multiplication rule for independent events to find the probability because of the fact that it's independent. So because they're independent, we're going to use this rule. So the probability of event E and F is taking the value that we found for probability of event E, which is 0.7, times the probability of event F, which is 0.6. And therefore, we would get the probability of E and F is equal to 0.42. And therefore, if we wanted to convert this to a fraction, then we would say that out of 100 times, okay, we would expect that the probability would be selected 42 times.